Hello everyone, I'm Michaela. We're here at APS 2025 and I'm here with our CTO, Yonatan Cohen. Yonatan, how is the conference for you so far?
It's been great. I was actually really looking forward to this conference. This is the biggest event for our community of the year, and it's really great to meet everybody and get to spend some time together and talk about the really amazing progress that we've seen in the field.
We just raised $170 million as well, so it's one of the largest funding rounds that this ecosystem, this community has seen. So how does this, from your perspective as a CTO, influence our technology roadmap?
So this is actually a very important step for us at Quantum Machines. It allows us to do two major things. One is to really accelerate our roadmap, in particular with emphasis on scaling up technologies for scaling up quantum computers and our next generation technologies. And second is to enhance our customer support activity, which is already one of the major things that we invested in, to support further and be real partners to our customers, again, with emphasis on supporting some of the biggest and most leading players in the field today.
So you're interacting a lot with this entire ecosystem, with the leading players. Do you see any technological themes or hurdles popping up that really influence the near-term and mid-term roadmap and development of quantum computing?
Yeah, so the first thing that we are continuously seeing is this increasing push to scale down the price per qubit, and scale up the density, so making things more compact. And also lower the power per qubit, for the control electronic systems that we're developing. Together with this trend, we're also seeing a huge trend that we need to continuously push the analog specifications of the control system. And these two things actually together introduce new challenges in the field, because pushing the analog specs while increasing the density, lowering costs per qubit, and lowering power per qubit is a combined challenge that we would really love to solve.
So how does classical resources and computation come in here? Because QM is very much known for their hybrid control approach.
Yeah, this is a great question. Actually, this is another one of the big trends that we're seeing. People want to integrate the quantum computers with high performance computing power, and with the entire data center, really. So we're seeing continuously this trend to continue to push the integration between quantum and classical further. And this is something at Quantum Machines we've been pushing for years now, actually, since we founded the company. And we're now really seeing this trend happening across the industry, in particular because we're start seeing the big players really aiming towards quantum error correction at scale. And when you want to do quantum error correction at scale, you really need to integrate supercomputing power with the quantum processing units.
So coming back to Quantum Machines' latest hybrid control solution, the OPX1000, can you elaborate a bit more in detail how it really enables operating 1,000 qubits and beyond?
Yeah, so to begin with, we went along with the biggest trends in the industry, and we pushed really strongly the channel density. We now have the highest channel density in the market for the control electronics. And at the same time, we pushed analog specifications to a new level with direct digital synthesis technology, which really allow us to improve the specifications of the electronics while lowering costs, increasing densities, and lowering power per qubit. And at the same time, we continue to push the core technology of Quantum Machine, which is this hybrid control, which is how we integrate classical computing with quantum computing. Both in terms of the hybrid processing unit that now has more compute power per qubit, more classical compute power per qubit, as well as the fast interfaces, the tight integration with GPUs and CPUs. Our work with Nvidia, for example, on DGX Quantum, that really pushes the integration with HPC to the limit.
So you've been already mentioning our hybrid processing unit. Can you explain on a higher level how it functions?
So on the highest level, the HPU, first of all, is responsible to create the sequences of quantum operations, which are the sequences of pulses that we send to the qubits to create the quantum operations. But then the reason why we called it a hybrid processing unit is that we've integrated that with general classical compute engines for the first time. And this opens up new possibilities for quantum classical workloads to be run very efficiently on the system.
Can you give a few examples what these workloads are typically?
Yeah, so this could be, basic calibrations of the system, which are almost always involve quantum operations and then classical operations that go back and forth. This could be feed-forward based quantum routines like adaptive state preparations of things of that nature. And it could go all the way to quantum error correction and hybrid variational algorithms. All of these different applications require both quantum operations to be run on the quantum processor, but also classical operations. And it requires this quantum classical loop to be very tightly integrated.
So help me understand one thing. Why is this tight integration between quantum and classical so essential for really achieving practical quantum computing and doing quantum error correction, for instance, at scale?
So on the very practical level, almost everything that we run on a quantum computer is actually really a hybrid quantum classical workload, okay? Meaning that we run something on the quantum processor, then we take the results, we run something based on this on the classical computation resource, and then we go back and forth, quantum classical, quantum classical. And in order to accelerate both the development and finally also the actual runtimes of the applications, we need this tight integration between the quantum operations and the classical operations. And that's what we do with hybrid quantum control.
Previously, you also mentioned the collaboration with Nvidia. How does the DGX Quantum now come in here? We have all this hybrid control within our hardware. Why do we need, to work with also other players in the field?
Yeah, so as I mentioned, we were the first to put classical compute engines into the heart of the quantum control system so that we can close this quantum classical loop very, very quickly within the control hardware and the QPU. But now, as we move forward towards quantum error correction, for example, at scale, and other applications at scale, we need more classical compute power to be tightly integrated with the system. So with Nvidia, we've created this very low latency and high bandwidth link from the control system to the Nvidia CPU GPU system. And that gives us an additional extra compute power that allows us to move towards a much higher scale of hybrid quantum classical workloads.
So you're bringing here really different technologies together. How do you experience, working with these different, platforms, and what's the challenge in, bridging really these different technologies, right? We have HPU, CPU, now GPUs.
Yeah, it's a great question because I think the next step of the quantum control industry or the quantum control system is to really become what we call the quantum control data center. So it's no longer just the quantum controller, just the HPU talking to the QPU, and it's no longer just general software talking to the quantum control. We really need to build integrated CPU, GPU, HPU, heterogeneous systems that are all made to optimize the work with the quantum processing unit. And finally, it also works vice versa, where the QPU finally gives us, extra compute power. And then we get not just the quantum control data center, but really the real data center with the QPU integrated.
And DGX Quantum is the first building block for this data center or for this ecosystem, or how should we think about this collaboration?
Yeah, I would say it's the first reference architecture for such a quantum control data center to be built, right? So, the super low latency link that we've built from the control system to an accelerator in the data center like the Nvidia GPU, CPU system. This is really a reference architecture for how you would build such a heterogeneous control / supercomputing integrated with QPU system, right?
What kind of workloads are we already able to run with this, or is this just really still work in progress?
So we're just launching it now. We have our early adopter programs that starts really just right now with really great customers on the list of first customers that we're going to try to use the system. And we already have big plans, both for neural networks that improve calibrations, quantum error correction benchmarking, and other hybrid quantum classical workflows that we want to run on the system. We've already sort of started benchmarking the first applications, both in neural network-based calibrations, as well as quantum error correction algorithms and decoders that we've implemented, but this is really just the first examples of what we can run on the system, and we really want to see how this grows in the next couple of years.
So we talked a lot about the hardware innovations. Let's now talk also a bit about software. So what is QM doing in order to make the software integration and just the operation of quantum computers more easy and scalable?
Yeah, so one of the things that I think our customers like the most about our system is our software layer, which, when we first introduced it, it was really easy for customers to start running their hybrid workflows, and in particular the calibrations, which is maybe 90% of what people do today to develop quantum computers. And what we're doing now is we're moving from enabling very quick and flexible development of single calibrations on a small number of qubits to developing really automated workflows that run on very large-scale quantum processors. And this is what we do with a new product that we call Qualibrate, which is an open source platform for defining those calibration workflows and automating them, and also managing the data for the system, etc. This is a big step for us because we really believe that it is the step that's necessary for us to continue to lead in this productive and flexible software for quantum control.
Can you elaborate a bit behind the philosophy of, we're a hardware company, right? We're making control electronics. Why do we also put so much emphasis on software in general and in developing these solutions?
For us, it's a huge value add to our customers. And the fact that, as you said, we're a hardware company allows us also to create all of these open source libraries with the emphasis on open source, right? So we see two major things beside our hardware, which are huge added value. First are these open source libraries and software infrastructure, and then our customer success services, which is something very unique that we've built with many physics PhDs and also software people that are really experts in quantum control and can really partner with our customers to help them implement those open source libraries on their systems. And the combination of these open source software, both infrastructure and calibrations and so on, together with our customer success team, is a huge added value on top of our dedicated quantum control hardware.
It really makes it very easy to get started, even if you're coming new into this field, which we're seeing a lot now, right? There are lots of newer startups and also people who are coming from different backgrounds, and then they need a new or an easy introduction into these complex quantum systems. Would you agree with that, or how?
Yeah, exactly. This is exactly right, and it really pinpoints the one of our core values. We care mostly about the success of our customers more than we care about even our products, right? Because the product is the mean to succeed in the real mission, which is to build a quantum computer, a useful quantum computer. So for us, we provide our quantum control hardware, but then we really want to make sure that our customers can embed those products in their systems and really succeed in integrating them and then running the required workflows on these systems.
So now that we've already been talking about core values, what are some of the values that you bring into your daily work as a CTO and into the technology branch of quantum machines?
So first, we've talked about this focus on customers. For us, this is a real core value because we don't believe that the greatest ideas come from just sitting in the basement. We really want to engage with the customers. They bring the real needs and the real insight into the needs. And so we put a lot of emphasis on working very closely with the customers and then focusing on their problems. This is where the real innovation, I believe, is coming from. And the second thing is, we try to be very ambitious about it. And these things go together. Once we identify a real problem, it doesn't matter what it takes to solve it. This is the problem that we need to solve, and we need to be very ambitious about our ability to solve this.
Thank you so much, Yonatan, for this discussion. And I look forward to the rest of this conference and everything that we have in store this week.
Thank you so much, Michaela.